Hello everyone, my name is Aiman Shah bin Muhammad Yusuf with the matrix number 230699. Alongside of me we have Lim Ai Chen 230926 and also Sophia Elia binti Rosli 229022. As you can see, the topic of our project on the numerical method, which is smart pump performance and cavitation risk assessment using MATLAB app design. Pumping systems are the unsung workhorses of industrial plants, but they also consume massive amount of energy. Today we'll show you how we use MATLAB to build a diagnostic tool that optimizes pump efficiency, targets cavitation risks, and aligns routine chemical engineering operations directly with global sustainability goals. Without further ado, let's dive right in.
Pumps are widely used in chemical plants, water treatment facilities, and many industrial processes to transport freight. However, a pump operated away from its best efficiency point, or BEP, its performance will decrease. As shown on the left side of the slide, operating away from the BEP can result in several problems, including increased energy consumptions, reduced pump efficiency, excessive vibrations, and cavitation, which may eventually cause equipment damage and higher maintenance costs. So to address this problem, we developed the Smart Pump Performance and Cavitation Risk Assessments app using MATLAB App Designer. So the main purpose of this application is to analyze pump performance using experimental pump data, determine both the operating point and best efficiency point, assess the cavitation risk based on the operating conditions, and provide recommendations to help user operate the pump more efficiently and safely. So at the bottom of the slide, you can see the overall application workflow. First, the user import the pump performance data from an Excel file. Next, the user enter the required system parameters, such as the static head and resistance constant K. After clicking Run Analysis, the application performs all numerical calculations automatically and finally display the result together with the cavitation risk level and recommendations. Overall, this application provides a fast, accurate, and user-friendly tools that assist engineers in evaluating pump performance while reducing manual calculations. This slide highlights the main features and benefits of our applications. So the application import pump performance data from Excel, automatically generate the pump and efficiency curve, calculate the operating point and the best efficiency point, and assess the cavitation risk. The interface is designed using MATLAB App Designer and consists of three main sections, which is import data, input parameter, and result, making it simple and user-friendly. Compared with manual calculations, our application provides faster and more accurate pump performance analysis, support energy-efficient operations, help prevent cavitations, and assist engineers in making better operational decisions. The first numerical method used in our application is regression analysis. First, the application calculates the pump efficiency using the hydraulic efficiency equations. Since the imported pump data consists of discrete experimental data points, it cannot be directly used for route finding or optimizations. Therefore, we use second-order polynomial regression with MATLAB polyfit function to generate continuous equation for both the pump head curve and the efficiency curve. So we selected a second-order polynomial because pump performance naturally follow a non-linear trend. For the efficiency curve, the efficiency increased with flow rates, reach a maximum value at the best efficiency point, and then decrease. This produces a parabolic shape that is accurately represented by a quadratic equation. A linear equation cannot capture this behavior, while higher-order polynomial may overfit the data and produce unrealistic oscillation. Therefore, the second-order polynomial provides a good balance between simplicity, accuracy, and computational efficiency. The output of this step are the continuous pump head equations and efficiency equations, which are used in the next numerical methods. The second numerical method is the Newton-Raphson method. So the purpose of this method is to determine the operating flow rates, which is the intersection between the pump curve and the system curve. The system curve is calculated using the static head and resistance constant entered by the user. We define a nonlinear equation where the pump head equal to the system head. And the Newton-Raphson interactive formula is then used to solve these equations with convergence is achieved. The output are the operating flow rates and operating head, which represent the actual operating condition of the pump. And the third numerical method is the golden section search. The objective of this method is to determine the best efficiency point, which is the flow rates that give the maximum pump efficiency. Our application minimizes the negative efficiency functions so that the maximum efficiency can be obtained. During each iteration, the search interval becomes smaller until the optimum flow rate is found. The output are the optimum flow rates and the maximum efficiency. And after determining the operating flow rate and the optimum flow rate, the application calculates the percentage deviation between these two values. If the deviation is less than 10%, the pump is classified as low risk, indicating stable operation near the best efficiency point. So if the deviation is between 10% to 20%, the pump is classified as moderate risk and regular monitoring is recommended. If the deviation exceeds 20%, the pump is classified as high risk, indicating a high possibility of cavitations and mechanical change. The application then recommends corrective action to bring the pump closer to its optimal operating conditions. And this slide shows the graphical user interface of our MATLAB applications. The application is divided into three main sections. One, the left is the import data section, where user import pump performance data from an Excel. The imported data include the flow rates, pump head, density, and power, which are displayed in the table. Below that is the input parameter section, where user enter the static head and resistance constant before clicking the run analysis. In the center, the applications automatically generate four graphs, which are the pump curve, system curve, the combined pump and system curve, and the efficiency curve. The combined graph clearly shows the operating point, while the efficiency curve indicates the best efficiency point. While on the right-hand side, the application displays the calculated operating flow rates, operating head, optimum flow rate, maximum efficiency, deviations, cavitation risk level, and the corresponding recommendations. The user-friendly interface allows engineers to analyze pump performance quickly without performing manual calculations.
Hello, my name is Sophia Elia. So in this video, I will demonstrate how our smart pump performance and cavitation risk assessment app works using three different cases. So firstly, we have to import the data by clicking this import Excel button and put in our data set. Okay, for the first case, we'll simulate a standard well-optimized system with a static head of 3 meter and resistance constant of 0.0025. Okay, then we will run analysis by clicking this button. And this is the result. We will start with the pump curve, a quadratic line of test speed through our raw manufacturer data. So the blue line here. At the bottom left, we can see a system curve shows a gentle quadratic slope starting right at our 3 meter static head mark here. And the graph here, we can see the blue pump line and red system line intersect precisely at our calculated operating point, shown by the yellow circle at 75.07 cubic meter per hour. And this is our efficiency curve. Our calculated operating point sits remarkably close to our absolute peak efficiency point at 70 cubic meter per hour. Since our deviation is only 7.24%, so the low risk banner will pop up here. Then we'll try to do this again using a different case, which is case 2. For case 2, we will remove the physical elevation lift and set it to 0, and resistance constant is changed to 0.09, means that there's still pipe friction. Okay, so we'll run the analysis. So we get the moderate risk here. As for the graph, we can see the system curve. System curve plot now initiate exactly at the origin, 0, 0, because there is no static head pressure to overcome. However, the curve climbs much faster due to increased resistance coefficients in our combined graph. This deeper red line now chokes the pump, pulling our operating point back to the left of our peak efficiency. Red lines now intersect at a lower flow rate of 57.79 cubic meters per hour. So because our operational point has migrated significantly away from 70 cubic meters per hour, which is our optimum point, the performance deviation has widened to 17.44%. So we will get the moderate risk banner here. Okay, for the next one is for the case 3, we'll change the static head to 3 and the resistance constant to 0.25. Okay, this simulates a heavily restricted pipeline network mimicking a severe line blockage or a nearly closed discharge valve. Okay, then we will run the analysis. So the graph changes and also the banner. Okay, for the graph, we can see the system curve. It skyrockets vertically, highlighting the extreme hydraulic resistance in the pipes. At the combined pump and system curve, we can see the intersection point is forced dramatically to the far left of the chart. The flow rate has been heavily choked down to just 38.79 cubic meters per hour. So we can see that our operating flow rate is far away from our optimal flow rate. Then the deviation also increased to 44.63%, indicating that our pump is at high risk. Okay. This warns the operators of imminent low flow fluid circulation, heat accumulation, and severe cavitation risk. Simultaneously, the recommendation Windows update with troubleshooting procedures to clear the bottleneck. So for the conclusion, as demonstrated across all three test cases, the app successfully maps complex mathematical curve fitting, visually isolates system intersection, and delivers immediate diagnostic feedback based on hydraulic principle.
Hi, hello. My name is Amar Shabuma Yusuf with the matrix number 230609. So, for my part, I'll be explaining on the contributions to sustainability and also planetary health. So, moving beyond the mathematics, let's look at how this tool drives process optimization and energy minimization. In any chemical plant, centrifugal pumps are major energy consumers. By combining multilinear regression with root finding optimization, our MATLAB tool dynamically steers the pump to operate right at its best efficient point. From a thermodynamic perspective, minimizing the power input for a required flow and heat directly reduces system irreversibilities and energy degradation. By squeezing out these inefficiencies, we lower the plant's overall electrical demand. Ultimately, this grid relief scales up to reduce regional utility emissions and greenhouse gases, showing how a local fluid mechanics adjustment directly translates into macro level environmental benefits and planetary health. Now we will be moving towards the next point, which is fluid dynamics and asset lifestyle. Let's see how this tool greatly impacts the management of it. In chemical processes, running a pump away from its design specs leads to serious fluid anomalies, most notably cavitation. When local fluid pressure drops below the vapor pressure, vapor bubbles form and violently collapse. These rapid collapses generate extreme localized shock waves that pit and erode the pump impeller over time. Our diagnostic framework acts as a predictive defense system, continuously monitoring operations to minimize cavitation and destructive mechanical vibrations. By keeping the pump healthy, we significantly extend its operational lifespan. In the bigger picture, this supports a circular economy by drastically reducing hazardous maintenance waste and conserving the raw materials, and energy typically required to manufacture new industrial machinery. This is also one of the most important point, which is the water energy nexus. Moving forward, let's look at the broader picture. As chemical engineers, we know that processes never exist in a vacuum. Pumping systems form the structural backbone of almost every chemical plant, water treatment facilities, and waste management network. Because water transport is completely dependent on energy, optimizing fluid flow inherently optimizes the resource usage. While improving a single pumping unit might seem like a small localized adjustment, these incremental savings aggregate into massive macro-level environmental relief when scaled across a whole chemical complex or regional supply chain. By using this tool to lower overall operational strain, we ensure that scaling up industrial throughput does not overload the local ecological life support systems that we rely on. Well, to conclude, this project ultimately highlights a critical shift in engineering values. Historically, chemical engineering success was measured almost entirely by maximum product yield and short-term economic gains. Today, our definitions have evolved. We recognize that chemical plants are open thermodynamic systems that continuously exchange mass and energy with the biosphere, which is the Earth. Because of this, our diagnostic framework elevates the role of the engineer from a simple technical troubleshooter to a true custodian of both technological and ecological systems. By treating planetary health as a primary design constraint rather than a later afterthought, this tool proves that even routine, local interventions like optimizing a single pump are vital steps in sustaining the global life support systems that we all depend on today. Thank you.